All right, cool. So it turns out there's this other way of doing this problem. And the other way of doing this problem is instead of thinking of it as a top bottom integral, when we think of it as a top bottom integral, we need to split it up into two pieces, right? But if you just turned your head to the side like this, you could think of this as a right left integral. And that's what we want to talk about next. So there's a big advantage to thinking about this as a right left integral. And that big advantage is that your integral doesn't need to be split into two pieces. So when you look at this picture I've drawn over here, the right left integral, I guess you got to remember that the bigger numbers are on the right, because the x values increase as you go from left to right, and the smaller numbers are on the left. So we're still doing bigger minus smaller, just like we did up above over here. Bigger minus smaller. The only difference is that your orientation is different. And our orientation is different because we are writing things, our functions where y is the independent variable and x is the dependent variable. So it's like your independent variable lives along the y-axis. And you're plugging in y values and the x values are popping out like this. Okay. So usually, instead of using a and b, we use c and d. Instead of using dx, we use dy. And everything is expressed in terms of y. All right. So if we were to redo example 5, when you think of it as a left-right integral, you don't have to worry about splitting it into two pieces. You do need to find the intersection points. So we found the intersection point to match our picture, which is 1. And then you simply subtract the function on the right from the function on the left. So I didn't label that function on the right there. So let me do that. This is going to be x equal to 2 minus y. And the function on the left, I labeled it up high there, but I could write it x squared. Oops, sorry, not x squared. We don't want to use x squared because x is not our independent variable. Y is our independent variable. So this is going to be x equal to the square root of y. And then we just subtract each of those. And find the antiderivative, plug in the result, you get the same answer. Does that make sense for everybody? Is there any questions about this? Why don't we try number 2 right now? Let's try that guy. So I'm going to give you a few moments to try this. Do we all know what this object looks like? Can someone in the chat box describe to us what this, tell the whole class what that x equal to y squared looks like? I don't think that's obvious. Anybody know? Well, it's a parabola that opens sideways like this. So this is x equal to y squared. I mean, this is y equal to x squared. X equal to y squared looks like this. Can't do it with my arms. Looks like this. So why don't you guys take a second to try this? We can actually do this one in 2 ways, but I think the first thing I would do is I would try to draw a picture. Then I would find the intersection points. Continue like that. Okay. So try that. Let me know when you finish. All right. So let me find these intersection points first. So I guess you really want to make sure that your function is written with the same independent variable. So if I have something like x equal to y squared, if I want to do it as a top-bottom integral, I need to write everything in terms of x. So what I can do is I can take the square root of both sides. So let's say I take the square root of both sides. If I took the square root of both sides, this would give me y is equal to plus or minus square root of x. Now, when you look at this blue graph over here, this blue graph is the top half of the blue graph is the square root function, the positive square root function. And the bottom part of the graph is the negative part of the square root function. And by looking at our picture, we really only need to worry about the top half. So really what I'm going to do is I'm going to ignore the negative one. I'm just going to keep the positive one. And I wanted to figure out what the intersection point right here is. So I'm going to set my two functions equal to each other. So I'm going to have one part be rad x, and the other part is just equal to x, right? And then what I can do is I can square both sides. When I square both sides, I'm going to get x is equal to x squared. And this gives me 0 is equal to x squared minus x, which is equal to x times x minus 1. So from doing that, I can see that my intersection points are going to be x equal to 0 and x equal to 1. Is there any questions about that? So when I go to label my graph, this part here is the positive square root graph. This part here is the negative square root graph. And this part here is just x. Okay. And I'm looking for, oops. I'm looking for this region right there. So if you have that set up properly, then you can solve your integral. You know that you want to do the integral, our region of integration we just found was from 0 to 1. And we want to do the, actually I plan to do this integral twice. So let me move this slightly. So first we'll do it as a top bottom. And when I'm thinking of it as a top bottom, that means that my integral is going to be in terms of x. And my top function is going to be rad x, and my bottom function is going to be x. So when I set up my integral, it looks like this. Does anybody have any questions about what I've written so far? You can definitely ask if you had any questions. No questions. All right, cool. Just to reiterate, first, I drew a picture to get a lay of the land. I found the intersection points. I decided to do it as top bottom, so I was looking for intersection points of x values. Because it's a top bottom integral, my integral is dx. That's what you're used to working with. The bigger function is going to be rad x, and the smaller function is going to be x. So I subtract the bigger minus the smaller, and I already found my regions of integration. Okay, so I think the next thing I should do is I should convert this to exponential form. and then find the antiderivative. And I guess the last thing I should do is plug in the endpoints. So that's the fundamental theorem of calculus. Was there any questions about, I don't know, integrating? This is kind of what your next quiz is going to be on. I think each class I do it faster and faster. I hope that doesn't bother you. Okay. Then we're just going to plug in the endpoints. So when I plug in the endpoints, I plug in a 1, I get 2/3. I plug in a 1 into the second term, I get 1/2. And then I get minus 0 minus 0. Do you have to write that? Not really, but I want to communicate the fact that I plugged in the 1 first. It subtracted what I got when I plugged in the 0. This guy is 4/6. This guy is 3/6. 4/6 minus 3/6 is 1/6. So we get 1/6 units squared. Does that make sense for everybody? Is there any questions about doing it as a top-bottom integral? No questions. Great. What I want to do next is I want to do the same exact problem, but I'm going to do it as a left-right integral. And when I do it as left-right integral, the function on the right, and first of all, when I do it as a left-right integral, everything needs to be expressed in terms of y. So y needs to be the independent variable. So when I look at this guy, the blue function is just going to be x equal to y squared. And the green function is going to be x equal to y. I guess up above, I didn't put the y equal to here. Let me put y equal to this and y equal to that. And this is y is equal to x. All right. So just like before, I need to find the intersection points. To find the intersection points, I set the two functions equal to each other. So I get y squared is equal to y. Then I subtract, I get y squared minus y is equal to 0. Then I factor, I get y times y minus 1 is equal to 0. And this tells me y is equal to 0 or 1. Y is equal to 1. When you look at the picture, this kind of makes sense, right? Here's the 0 y value and here's the 1 y value. So it looks believable. Any questions about that? So now we're going to do it as a right-left integral. And we're going to integrate. Because we're doing it as a right-left integral, the variable of integration will be dy. The smallest my y value can be is 0, and the biggest my y value can be is 1. The bigger function's on the right, so the bigger function is y, and the smaller function's on the left, so that's going to be minus y squared. Is there any questions about that? All right, so now we just find the antiderivative. The antiderivative of y is y squared over 2. The antiderivative of y squared is y cubed over 3. And I want to plug in a 0 and a 1. So when I evaluate this integral, it's going to be 1/2 minus 1/3. That's what you get when you plug in the 1. Minus 0 minus 0. That's what you get when you plug in the 0. And you end up with 1/2, which is 3/6, minus 2/6 is 1/6. So you get 1/6 units squared. Does So that's how you do it as a left right. So which one do you think is easier, top, bottom, or left, right? Any thoughts? Anyone have a preference? See, it's funny, like people privately message me, they like top, bottom better. Even though to me, I think left, right is easier. It's less solving. You don't have to work with square roots. You don't have to change to exponential form because it's already an exponential form, but you're used to working with top, bottom. So it seems easier, I think. That's my guess. I don't know. All right, cool.